Okay, now that you know how to use histograms, dot plots, and box plots to represent data, let's look at what you can conclude or summarize from those data sets. We'll look at center and variability, which are important, and then we'll look at how making decisions in the real world can be driven by looking at those kinds of things like box plots and histograms and dot plots. And then we'll look at some gotchas. So let's look at first at center and variability. Here is a dot plot of a number of students who read books over the summer. And you can see that each dot represents one student. So it looks like 3 students read 4 books over the summer, and 3 students read 6 books over the summer. 2 students read 12 books over the summer. You get the idea of a dot plot. And we can start to make certain observations just by looking at this dot plot. And that's why graphing things on dot plots and other kinds of graphs is so important. We can see, for instance, that most common number of books read was how many? Well, we can just see easily here from the dot plot that it was 5. Okay, so 5 books was the most common number. Most of the data ranges from what to what? We can see that most of it is clustered right here. So between, let's see, 4 and 8 books, we can fill that out. And then finally, there are 2 outliers at how many books? We can see that most of the data are here, but there's these 2 students who read 12 books over the summer. So we can go ahead and fill that out. Now, why is this important? Well, if you were just to list all of these data here, you wouldn't be able, as numbers, you probably wouldn't be able to call these things out. But what you want to do is be able to tell people when you do a study or any sort of thing where you're displaying data, you want to be able to tell them what the meaning of that data is. And you can see that the meaning here is that the most common number of books was 5. Most of the students read between 4 and 8 books. And there were 2 students who read 12 books. So that was really impressive. And that's all from just looking at the dot plot here. Now let's look at how you can make decisions in the real world by looking at data. Romani is a professor studying the effects of 2 medications designed to control the presence of an enzyme in the bloodstream. Okay, so she's looking at 2 different medicines, and it's to help you to understand what a certain kind of a chemical, an enzyme in your bloodstream, how much of that enzyme there is. And she has gathered these following data. So let's go ahead and look at this first one. This one's about medicine A, and you can see she's got a dot plot here, and we'll read the details off of this dot plot in just a second, but you can see this is medicine A's data. And then we can look at medicine B's data right here. Okay? So automatically you can see that medicine A and medicine B from the 2 different box plots are pretty different. Let's see how they're the same though first. So medicine A, what was its median? Well, remember the median in a box plot is that point that's inside the box. So we can see that that median is 23. So we can fill that out. How about medicine B's median? We look here inside the box. Here's that point. That's the median. Ah, it's also 23. So now that's really interesting. Both of these medications had a median enzyme count of 23. So some people might conclude, well, the medications are identical. They give you the same kind of an effect on your blood. But clearly these 2 graphs show that medicine A and medicine B are actually quite different. That would be important for Romani or any of the doctors using these medications or any of their patients to know that, right? So we need to also understand what the measure of the spread of the data, the variability of the data are. And so let's go ahead and find out what medicine A's interquartile range is, okay? So remember, that's when we use a box plot, that's the measure for spread that we use is interquartile range. And that's the difference between the lower quartile, which is the left side of the box, and the upper quartile, which is the right side of the box. So the lower quartile here is, let's see, it's between 21 and 23. It looks like it's 22. And the upper quartile is 25. So the difference between 25 and 22 is 3. We'll go ahead and write that down here. Now, how about from medicine B? Well, medicine B, you can see the lower quartile is 19, and the upper quartile is, let's see, 27, it's 28. So 28 minus 19, so its interquartile range is 9. That's a much bigger variability for medicine B. Okay, so now we can ask ourselves important questions for Romani or doctors or patients. Which medicine is more consistent? Which gives you a more consistent enzyme count? Well, from these box plots, you would have to say that medicine A is more consistent because it gives you the range of results is a much tighter range. It doesn't give you results that vary so much and are so spread out. And this is exactly how statistics is used in the real world. Now let's look at just a couple of gotchas that you also want to pay attention to. The first is outliers. Let's look at this example. Sari's violin instructor recommends that she practice consistently 30 minutes every day. Sari practiced the following minutes during the last week. 5 minutes one day, 5 minutes the second day, then 7 minutes. Then she had a marathon practice session of 165 minutes, then 5 minutes, then a 17-minute day, and then 6 minutes. Okay, so let's start to analyze this data. Her median, if you were to line these all up from lowest to or least value to greatest value, the middle value would be 7 minutes. Okay, her mean, however, if you added all of these numbers up and divided by, let's see, there's 7 data points there, divided by 7, would be 30 minutes. So Sari says that she practiced the right amount because of the mean being 30 minutes. It's 30 minutes. Her instructor asked her to practice 30 minutes, so she did what she was supposed to do. Is she being accurate when she makes that statement? Well, the fact of the matter is there was a big outlier here, 165 minutes practicing that one day. Most of the days, though, she wasn't even close to 30 minutes. And that's where the median might show a better measure of what she was actually doing. So in the most times, she was doing around 7 minutes, not 30 minutes. And her instructor would probably say, that's not what I wanted you to do, because I want consistent practice for 30 minutes every day. So that's one example of how an outlier can kind of throw off a mean. And you might want to also look at the median to understand what's really going on with the data. Let's look at one other kind of a gotcha. This is called bimodal data. A mode is just a place where the data are kind of clustered around. So let's look at 2 different histograms here. Here's one histogram where there's kind of an even distribution with a peak in the middle. And then here's another histogram where there's a mode over here, one cluster, and then there's another cluster over here. So there's 2 modes, like bicycle has 2 wheels. This has 2 modes, so we call it bimodal. Well, we can ask ourselves, these data have medians in the same range. So probably the median for this data set is somewhere in this range. And it might be right here for this range too. But does that tell the whole story? If you were to say data set A and data set B here are pretty much the same because they have the same median, would that tell you what you need to know? Probably not. You'd have to also point out how they vary, and in particular how this second data set seems to have a cluster down here and a cluster up here, which is very, very different, even though it has the same median, from this data set up here. And you'd want to make sure and point that out.